Good morning, everyone. I will be presenting the last modification we made on the Truss network analysis, and we called it Truss membrane analysis because we introduced a membrane element that accounts for membrane forces inside the vault in the classical Truss network analysis. So the Truss network analysis is based on the limit analysis of arches and vault, which has been formulated by Hyman in 1966, and is based on three main assumptions. These are that the stone has no tensile stress, no tensile strength, sorry, meaning that we are neglecting the tensile stress strength of masonry. The second assumption is that we are considering an infinite compressive strength on stone. This actually is not a safe assumption, but however, for arches and vaults, the stresses are usually much lower than the strength of the material. And then we also are under the assumption that sliding between stones cannot occur. This also is not a safe assumption, but considering that usually the thickness of this structural element is very low, and with this small thickness, the axial force is usually within the cone of the adhesion, according to Kuhlmann model for adhesion. Then we can consider then that sliding usually never occurs in arches and vault, and actually it is very rarely observed in reality, and happens only when the structure is subjected to very high concentrated loads, or it is very thick, which is, however, a very rare occasion in this kind of structure. So under this hypothesis, the only possible mechanism between two stones is that of a relative rotation about either the extrados or the intrados of the structure. And so we have the possibility of a mechanism under constant load, meaning that the behavior of this kind of structure is actually a ductile behavior. And so we can extend the limit analysis that is usually holding for plasticity models also to the statics of this kind of structure. And so based on this hypothesis, Hyman formulated the safe theorem for the structural analysis of vaults that says that if we are able to find a truss line fully contained within the thickness of the vault, then the vault is safe, or vault of arch, of course. And this is a small demonstration of this concept. This is a small arch model in which the Vassois have a curved interface so that they touch just in one point. And in this way, you can visualize the point where the axial force is transmitted between the Vassois of the arch. And you can see how the configuration of the arch modifies according to the applied load. Actually, here and here, I'm applying concentrated force to the arch. The arch deforms, and this is because the Vassois rotate one with respect to the other, and you can visualize the path of the force transmitted within the structure. So a generalization to the two-dimensional structure, which are the vaults, is the so-called truss network analysis. So instead of finding just a funicular polygon of the applied loads on the structure, we are looking for a funicular network of forces inside the structure. So usually for a vault, which is much more complex than a simple arch, we are looking for a surface that is funicular of applied loads that is fully contained within the thickness of the structure. And this surface is, of course, has an internal part and a boundary. The boundary can be divided into two parts, one that is supported and the other one which is free. And the free part of the boundary is what is called the free edge of this truss surface. It is discretized by a lattice model, and this is what we call the truss network. And in the truss network, of course, we divide a network of forces is composed of branches and nodes. Branches represent the axial force transmitted between nodes, and nodes are places where we are applying concentrated loads on the structure. So the first model of this kind was formulated by O'Dwyer in 1999, then developed by Bloch and introduced in Rhino's Volt, which is a plugin for Grasshopper that works on Rhino. And it was largely popularized among the scientific community. And so many believe that this approach was actually invented by Bloch, but it is just an implementation of the O'Dwyer approach. And then there are further, there was a further evolution of the truss network analysis. And the last and most interesting one, of course, is the one by me and Professor Rosati, in which we included the possibility of applying horizontal forces, and we described how to handle the free edge of the volt. And today I'm talking about a further extension of these methods, in which the truss network is substituted by a truss membrane. And this is done by including a triangular element inside the lattice of the network. And this allows to compute also membrane forces inside the model of this this truss surface. So what is the data that we need to analyze this kind of structure? First of all, we have nodes and branches, as I told you. Nodes are characterized by a position and applied forces. Branches are characterized by a truss value, which is the axial force transmitted between the nodes. And we are adding, because since we are adding membrane elements, we are also adding a membrane truss tensor, which is the membrane force tensor typical of membrane elements. Equations that we are using, since we are in the framework of the limit analysis of structure, mainly in the safe theorem, we only care about equilibrium, we don't care about compatibility, and so we are using only static equilibrium of nodes. And because we want to model also the membrane elements, we add a relationship between the membrane truss tensor and the truss forces inside the branches. And we will see that this is based on a virtual work equivalence. The unknowns of the problem are the truss in branches, the vertical position of nodes, because we want to find a configuration of this truss membrane that has to lay inside the thickness of the volt. And for the free edges, we don't know, we have as unknown the complete set of coordinates of the nodes, because for the free edges, since we don't have external forces applied to the volt, we need that this edge is actually funicular, not only of the vertical forces applied to the structure, but also of the thrust transmitted by the interior of the structure. And also we have some constraints, and this constraint says that the truss membrane has to lie inside the thickness of the volt, and the force transmitted by branches has to be compressive, because we have a unilateral material model. Actually, those of you that are used to finite element analysis usually model the geometry and the mechanics of the structure by finite elements. These are not finite elements, so they do not model both geometry and mechanics. They just model somehow the geometry by the constraints and the forces inside the structure. How can we use this kind of analysis? We can use it by verifying the existence of the truss forces which are inside the structure or truss membrane forces that are in equilibrium with applied forces, or we can use it to find a maximum multiplier of some applied load, and so to perform a limit analysis of the structure, or to find the minimum thickness for that structure. Actually, this is an interesting application because usually in masonry walls and arches we are computing the so-called geometric safety factor, which is the ratio between the actual thickness of the structure and the limit, the smallest thickness that allows the existence of this truss membrane inside the structure. And so how do we build the equilibrium equations that we use to solve this problem? We just apply an equilibrium at nodes, written at nodes. So this is very easy to apply, and we have applied forces and thrust coming from the several nodes that converge to each node. Of course, this thrust is represented by the letter T, which is a scalar value, and C, which are the cosine directors of the branch. This equation is slightly modified by introducing a reference thrust, horizontal thrust, by means of this relationship. So the thrust inside the branch is related to its horizontal component by the projection on the horizontal plane, and also by introducing this zeta, scalar zeta, that will allow us to modify and to optimize the solving procedure to find a different kind of solutions. The two solutions that we are interested in are the solution so-called minimum and maximum thrust, because since we are applying a limit analysis and only static conditions, equilibrium conditions, we are actually interested in finding an interval of possible equilibrated solution, all contained within the thickness of the structure. And of course, in the limit condition in which the structure has reached a limit equilibrium state, which is, for example, minimum thickness, in that case, the maximum and minimum thrust solution are coincident one each other. And so in that case, we realize that we reached this limit condition by verifying that the value of zeta for both the maximum thrust solution and minimum thrust solution are equal one each other. And I will use this concept later to show that, to evaluate the minimum thickness of a vault. So basically, we are splitting this set of equations into two sets of equations. One represented the horizontal equilibrium and one represented the vertical equilibrium. They are apparently equal one each other, but in case the structure is subjected only to vertical loads, you see that in the horizontal equilibrium, the effect of the horizontal force is zero. And so you can solve this equation only to evaluate the thrust values inside the structure. Once you have these thrust values, you can use them to define some thrust densities and use the force density method to solve only the vertical equilibrium of the structure. And so in this case, you can have the coordinate of the nodes, the vertical coordinate of nodes, and consider these as unknown of the problem. And so written in matrix form, you have these two sets of equations, means of this zeta. It is considered considered as an unknown in the second set of equation. Only vertical loads, this simplifies and you can solve it in for just the thrust values here. However, we are considering horizontal loads. So in that case, we are solving both equations iteratively. First solve this equation by choosing a tentative value of zeta, and then use this solution into the second equation and update the value of zeta. And then we go back to the first equation and solve it iteratively. And this is described in this solving procedure. So we input the known values, which are the horizontal position of nodes, the limits for the vertical position of nodes, limits for the thrust values in branches, and limits for the thrust membrane forces. Then we iteratively solve that set of equations. And basically, if we don't have boundary nodes, meaning that the volt is supported on the entire boundary and there are no holes, then we can solve the linear optimization for the horizontal equilibrium. We have the thrust that has to fulfill some equations. And once we have the values of the thrust inside the volt, we can do the vertical equilibrium and solve for z, which is the vertical position of nodes, and zeta, that is that parameter that allows us to find solution of minimum and maximum thrust. If we have free edges, we have to add a few equations to evaluate the horizontal position of nodes, and this is made basically by application of the force density method applied only on the free boundary of the structure, so that we are able to compute the horizontal position of nodes on the free boundary of the structure. This procedure, of course, is iterated until we reach convergence, that is attained when two consecutive values of that parameter zeta are coincident with each other relative to a given tolerance. As I told you, the extension regards the equivalence between thrust force tensor in triangular elements and thrust values on the branches that represent the perimeter of this triangle. And so the first step is that we can verify that if the membrane modeled by this triangle is not subjected to any external load, then forces transmitted is a planar system of forces protect the sides of the triangle. Actually, these forces can be represented by this projection, which is also in equilibrium. So on each the component on a singular on one of the branches that converge to that node is equal and opposite to the same component on the other node. That this can be verified by simple equilibrium equations representing the rotation about one of the nodes of the triangular element. Then we have to set an equivalence between the thrust values into the branches and thrust tensor, which is just a membrane force tensor, expressed here in Mandel notation. And this is the virtual work associated to the thrust tensor for a virtual strain tensor. And since everything is constant on the triangle, this work is easily computed as the area of the triangle times the dot product between these two tensors. And then the virtual work associated to the thrust values in branches is simply the length of each branch times the elongation of the branch times T, which is the thrust into the branch. Then we have equivalence between the elongation of branches and the strain tensor inside the element. And this is obtained just by projecting this stress tensor on the branches, meaning that we are computing the elongation according to this strain tensor. And this allows us to find a relationship between the elongation of branches and the strain tensor inside the membrane element. This is done by means of this projection tensor V. And then the relationship between thin branches and thrust forces into the membrane is easily computed by writing the equivalence into the two. And so we have the direct relationship between these two quantities. And so we can transform thrust membrane forces inside the triangular membrane element into thrust forces into the network represented by the sides of this triangle. Then we need to implement, of course, these quantities into the equilibrium, horizontal and vertical equilibrium equation, and this is just by adding the assemblage of some quantities that are added into the coefficient matrix of both equation, horizontal and vertical equation. Of course, these are slightly more complex than the case of a classical network, which has just a two-component vector to assemble, but it is an easy task if you are used to finite element implementation. And so the application that I will show you regards a vault that is in Baia thermal baths. Baia is a city near Naples. And the vault is the so-called Temple of Mercury. This is a dome built in the 1st century before Christ. And actually, it is thought to be a prototype of the Pantheon in Rome, because the size of this vault is just half of the Pantheon. It is the oldest dome we know of this side, which is of these sides, which is still standing, and is very similar to the Pantheon because of the geometry and because of the central oculus. But there are also additional 4 openings the sides of this vault, but these were made later, not by the Romans. Another characteristic of this vault is that because of the bradysism, we have that the floor of the vault is flooded by seawater. And so actually here the survey of the vault was quite complex, and actually we had to use a small boat to survey the vault. This is the cross section of the vault, this is the sea level, and this is the ground that flooded over the vault, because the original floor is 6 meters below the sea level. And these are a few geometric information about the vault. What is interesting is the material, which is concrete. It is not made of stones, but it is made of to the Pantheon. The geometry, as I told you, is similar to the Pantheon. It is larger than the Pantheon, at least near the oculus. This is the thrust model. It is composed on the triangular element for the inner part of the vault, and then the edge of the openings is modeled by branch elements, because usually we expect to have higher stresses on these edges, and so this is modeled by branch elements just on the free edges. And then the loading applied to this model is just the self-weight of the vault, because there is nothing on the top of the dome. It is not accessible, and so we're using just this density for evaluating the self-weight. These are the geometric solution for minimum and maximum thrust, and as you can see, the minimum thrust is deeper than the maximum thrust solution, as it happens in arches. The free boundary has changed completely. The coordinates of the edge nodes are unknown, and they form actually an arch that is funicular of the thrust coming from inside the vault. And thanks to that geometric equivalence, we are also able to find and compute the membrane force tensor. Here is represented by color shades the two principal membrane force values. And you can see the effect of the opening in lowering the stress in the part that is above the opening. Okay, then we perform that an analysis. Oh, sorry, I forgot to say something here. We can evaluate the difference between the two solutions, minimum and maximum thrust, by monitoring the ratio between the value of zeta for the deepest solution over the value of zeta for the shallowest solution. So having this ratio equal to 1.48 means that these two solutions are very different one each other, because they correspond to a different multiplier of the horizontal thrust. So actually this is proportional to the ratio between the total horizontal thrust transmitted to the supports. Then we reduce the thickness. Of course, the reduction of the thickness also lower the applied load, so you will see lower thrust values inside the vault. And solution for maximum thrust for 3. I recall that the original thickness is 0.75 meters. So it is more or less 2/3 of the original thickness. The ratio now is approaching 1. And you can see visually that the two solutions are equal, both from the geometrical point of view and from the thickness point of view, from the stress values point of view. And of course here you can see only blue shades for the stresses, meaning that in this solution they are all lower than the original, the thrust values corresponding to the original thickness of the vault, but this is because, of course, reducing the thickness, also the weight of the vault is lowered accordingly. And so this is just the conclusion. The next step will be that of analyzing another vault that is in biothermal baths, which is the so-called Temple of Venus, which is actually, it was an entire vault, but half of this vault just collapsed. And the vault is that it is represented by a pointed shape. It is the oldest pointed shape vault known, still standing, at least in part. Thank you.
I have a question concerning, I'm not sure if I understood you correctly.
Yeah.
But, did you add an additional membrane stiffness, or did you just having the thrust forces? Do you just recompute the equivalent membrane stresses? Or?
So first of all, I don't add any stiffness because I don't have material information regarding the vault. So there is no stiffness involved in this formula. We have only equilibrium equations. However, the equilibrium equations are not enough to fully define the distribution of thrust values inside the vault, and so we are solving the problem as an optimization problem, because we have less equations than unknowns, but we also have some constraints. So this is why we are not using any stiffness information. We have the framework of the safety theorem of the limit analysis. And we are not adding the element to the network. We are using that element to define and to interpret the thrust values in nodes, in the branches that are on the boundary. So the first step is to assign, excuse me?
So it is sort of post-processing.
It is also a pre-processing, because we need these equivalents in two steps of the analysis. First, to define the limit value for the thrust. So if we want some part of the structure to work under some stress distribution, we can control that by assigning these limits for the thrust values. But we have membrane limit values, and so we can use that equivalence to find the thrust corresponding to the to that membrane limits. And this is a pre-processing, and then we have post-processing interpreting the solution. So we have a distribution of thrust inside the network, and then we can interpret these thrust, which are actually axial forces, and interpret them as membrane forces.
The sides of the triangle is set how?
As infinite elements. I mean, there is not a general rule. It's just up to you.
To the sides of the
no. The topology of the model can be related to the stereotomy of the vault. For example, if you expect to have some alignments of bricks, you can set your elements according to the orthogonal and parallel direction of the bricks, and so that you can compute
the solution.
This affects the solution, yes. So you can somehow include the stereotomy of the vault into the solution.
And this is considered in the application. It is considered the lack of knowledge on this.
If you don't know this, then you have to.
So you should do a parametric analysis on.
Yes, on the possible organization of branches, topology of branches. But somehow you can adapt this to the stereotomy if you know the stereotomy, of course. But this was in the case study I showed. This is not applied because this is a concrete vault, so there are no bricks. It is just concrete. And actually, some information is here. No. Okay. It is just concrete, with some tough blocks inside, but they are not organized in any way.
Okay. But nevertheless, you use the first kinematics that you showed. So what is the relation between this and the kinematics that you showed at the beginning? With the stones?
Oh yes, the relation is that actually you can have cracks opening into concrete, and that crack allows a relative rotation between the two parts. So you can still use this model. But this model is just to justify that actually the behavior is ductile. That also happens in the bending behavior, even in no-tension material, is usually ductile because you have crack openings and relative rotation. But of course, the complete behavior is ductile because of sliding. So if you are able to verify that sliding is not occurring for the distribution of stresses that you found, then it will not occur, of course.
Is there any sensitivity to the side?
There is a very small sensitivity after a certain refinement of the mesh. We made a parametric analysis in this sense for a cross fault. Not much the sensitivity, if elements are small enough. There is the strongest sensitivity is on the topology. So if you choose a certain orientation of branches, these influence the solution.
For the concrete dome, the topology is the topology of the fracture.
The topology is, in the model is represented by the connection between the nodes. Yeah. So you can choose, so in this case, or in this case, everything is represented by meridian and parallel elements and diagonal elements which are set in both directions. If I choose, let's say, a random or a, let's say, less regular this organization of elements, I can have a slightly different solution. Not in this case because symmetry is governing the problem here, but in more complex geometries I can have slightly different solutions. This happens, for example, in cross vaults like these ones, because here you are expecting that each part of the vault is working as an arch in this direction, right? And is not working much in this direction. So you are orienting your branches according to these two directions. But you can also imagine that there is some thrust also in the direction parallel to the ribs, right? And so if you also include these additional branches, you have a slightly different solution. And so usually you should look at the stereotomy, if you can look at the stereotomy, or consider different topology of the model and look for and since you are within the safe theorem of the limit analysis, you can choose the one that maximizes the multiplier of the applied load. Because, however, it is the safe theorem, so you are reaching the limit from below, so you can maximize everything.
So you are using a static approach?
Yes, it is a static approach.
Right, and so in a conservative way, you have a solution that
yes, is conservative, yes.
This is good for such.
Of course.
You are sure you are not too far away from the correct solution?
I mean, I'm not sure I'm too far from the correct solution, but one way to look this is to verify this ratio. If you reached one then the two maximum and minimum Truss solution are coincident one each other. But this is not a proof that you are near the limit. You should also make another analysis, which can be a kinematic analysis, which is based on the unsafe theorem of the limit analysis. And in that case, you can compare the two solutions. And this is the only way.
So you have work to do?
Yes, this is done by another approach, which is the so-called discrete element method, in that case, which is based on the kinematic theorem, but it is a different approach, completely unrelated from this one. I cannot solve every problem, of course, but many people are working on that. For example, Emanuele is working on that. He is finding the kinematic solution for the collapse mechanism.
The same problem you can
but from different sides, yes. Okay. Thank you.